Now let us prove the fundamental theorem of arithmetic. The problem statement is given as if n is an integer greater than 1, then n can be written as the product of primes. Now let us get it into the solution. Let P of n be the proposition that the value n can be written as a product of primes. When it comes to the basis step, in the problem statement, it is given as n is greater than 1. So we have to take base value as 2. So we check it for P of 2 in the basis step. Since 2 itself is prime, P of 2 holds. Now in the inductive step, the inductive hypothesis is that P of j is true for all integers j where j values are from 2 to k. Now, with this hypothesis, we have to show that P of k plus 1 also holds. That is, k plus 1 can be expressed as product of primes. In order to prove P of k plus 1, we have to consider two cases, that is, k plus 1 as prime number and k plus 1 as composite number. Now let us take case 1. Here k plus 1 is prime. The only factors are itself and 1. Hence P of k plus 1 is true. When it comes to the second case, here k plus 1 is composite. It can be written as a product of two positive integers, let us say a and b, which takes the values from 2 to k. Since both a and b are integers with values at least 2 and not exceeding k, by inductive hypothesis, both a and b can be expressed as the product of primes. Hence, k plus 1 can also be written as product of primes. Now this we can extend for any integer n whose value is greater than 1. Since k plus 1 can be written as the product of those primes, by expressing it as a product of two integers a and b, the same can be done for any integer n. Hence, it is proved for P of n also. Now let us try by taking two examples. First, let us consider k is equal to 11. Now k plus 1 will be 12. 12 can be expressed as product of two positive integers in two ways. In the first way, it is 2 into 6. Since 2 is a prime number, P of 2 is true. P of 6 is also true because it can be expressed as product of two prime numbers, that is 2 into 3 is equal to 6. Hence, 12 can be expressed as 2 into 2 into 3. Now let us take the second way, where 12 can be expressed as 3 into 4. P of 3 is true because 3 is prime number. Now when it comes to the 4, P of 4 is also true because 4 can be expressed as product of 2 into 2. Now k plus 1, whose value is 12, can be expressed as 2 into 2 into 3. Hence, P of 12 is also holds. Now let us take k value as 12. Then k plus 1 becomes 13. 13 is prime, hence p of 13 is also true. So the concept that which we have proved for p of n with the examples of k being a value of 11 as well as 12, we have shown that it holds. Now let us consider one more example where we have the amount of postage of rupees 12 or more. We have to form using just 4 rupee and 5 rupee stamps. That is for any amount which is greater than or equal to 12. You have to form using just 4 rupee and 5 rupee stamps. Let us get it into the solution. As usual, P of n be the proposition function. That post of n rupees can be formed using only 4 rupee and 5 rupee stamps. Now let us get it into the basis step where P of 12, P of 13, P of 14 and P of 15 holds. This is why because P of 12 can be formed, that is the 12 rupees can be formed using 3 4 rupee stamps. P of 13, that is 13 rupees, can be formed using 2 4 rupee stamps and 1 5 rupee stamp. Similarly, 14 rupees can be formed with 1 4 rupee stamp and 2 5 rupee stamps. 15 rupees using 3 5 rupee stamps. Now you observe the pattern here. We started 12 rupees with 3 4 rupee stamps. When it comes to 13, the 4 rupee stamps are decreased by 1 and 5 rupee stamp is increased by 1. When it comes to the 14, it is further decreased by 1 and 5 rupee stamps further increased by 1. And for 15, we have all three 5 rupee stamps. The same can be extended now further also. P of 16, that is 16 rupees, can be formed using 4 rupee stamps. 17 by decreasing 1 4 rupee stamp and by increasing 1 5 rupee stamp, it can be expressed as 3 4 rupee stamps and 1 5 rupee stamps. 18 with the 2 4 rupee stamps and 2 5 rupee stamps and so on. Finally, 20 rupees you can form either using 4 5 rupee stamps or 5 4 rupee stamps. So here these things will follow a pattern which will be useful for us further to prove certain things. In inductive step, the hypothesis is that P of j holds for all values j taking from 12 to k, where k is greater than or equal to 15. By assuming this hypothesis, now we have to show that it also holds for P of k plus 1. Now let us use the inductive hypothesis. As per it, P of k minus 3 holds since k minus 3 is greater than or equal to 12. Let us take k value as 15 because k is greater than or equal to 15. Then k minus 3 will be 12. When we take k is equal to 16, k minus 3 will be 13. Now, the postage of k plus 1 rupees. To form it, the difference between k plus 1 and k minus 3 is 4. Hence, we can form the postage for k plus 1 rupees by just adding a 4 rupee stamp to the postage for k minus 3 rupees. Similarly, we can extend this proof for all n values greater than or equal to 12. And finally, we conclude that it holds for P of n where n is greater than or equal to 12. My dear students, now you pause this video and prove the same example using mathematical induction. After completion of your proof, you play this video and verify your proof against the proof given here. The problem statement will be the same. That is, any amount greater than or equal to 12 rupees can be formed using 4 rupee and 5 rupee stamps. Let us get it into the solution. Let P of n be the propositional function that postage of n rupees can be formed using 4 rupee and 5 rupee stamps. In the basic step, here we prove only for P of 12. That is, postage of 12 rupees can be formed using 3 4 rupee stamps. Here you can clearly observe that in strong induction, we have proved for P of 12, P of 13, P of 14 and P of 15. But in mathematical induction, in the basic step, we prove only for P of 12. In inductive step, the inductive hypothesis is taken as P of k is true or holds for any positive integer k, that is, the postage of k rupees where k is greater than or equal to 12 can be formed using 4 rupee and 5 rupee stamps. By assuming the inductive hypothesis, that is, it holds for P of k, we have to show that it also holds for P of k plus 1. For this, we need to consider two cases. In the first case, if at least one 4 rupee stamp has been used, then a 4 rupee stamp can be replaced with a 5 rupee stamp to yield a total of k plus 1 rupees. Now let us take the k value as 12, where we have used or formed the 12 rupees using 3 4 rupee stamps. Now, in order to form for 13 rupees, a 4 rupee stamp you can replace with a 5 rupee stamp. Now, for 13 rupees, it becomes two 4 rupee stamps and one 5 rupee stamp. Similarly, when you take k is equal to 13, to form for 14 rupees, 13 rupees is formed using two 4 rupee stamp and one 5 rupee stamp. Now, from 13, one 4 rupee stamp, you replace it with 5 rupee stamp. With this, the 14 rupees can be formed using one 4 rupee stamp and two 5 rupee stamps. In the second case, where we are not having any 4 rupee stamp in K, where we have to replace 3 4 5 rupee stamps can be replaced with 4 4 rupee stamps to yield a total of k plus 1 rupees. Now you take k as 15. 15 is formed using 3 5 rupee stamps. Now this 3 5 rupee stamps you replace with 4 4 rupee stamps to yield the formation for 16 rupees. Now the same concept can be extended for all n values greater than or equal to 12. Hence, P of n holds. Now let us come to well-ordering property. This property we have already used to prove the validity of the mathematical induction. You can also use the same property to prove the validity of the strong induction also. This property states that every non-empty set of non-negative integers has a least element. That is, whenever a set is not empty, then you can find a least element and the set has to be of non-negative integers. Now when it comes to the characteristics of this property, it is one of the axioms of the positive integers. This property can be directly used in proofs and it can be generalized. Now a definition for this well-ordering property is that a set is well ordered if every subset has a least element. It states that when we call a set as well ordering is when you form a subset from this set, it should have a least element. The examples are n is well ordered under less than or equal. From n, if you form any subset satisfying the condition less than or equal, it will be well ordered because certainly it will have a least element. Similarly, the set of finite strings over an alphabet using lexicographic ordering is well ordered. The lexicographic ordering says the way we have the words in a dictionary. That is, we'll have them alphabetically. When you take any subset of these finite strings, certainly it will have a least element. Hence, the set of finite strings over an alphabet is well ordered. Now let us use the well ordering property to prove the division algorithm. This division algorithm states that if A is an integer and D is a positive integer, then there are two unique integers Q and R satisfying the property that its values lies between 0 to D minus 1. Then A can be expressed as A is equal to dq plus R. Here you have to understand the characteristics of each variable. A is an integer, D is a positive integer, Q and R are unique integers. Here you can take Q as a quotient and R as a remainder. Now the integer A can be expressed as D into quotient plus remainder. Now let us get into the solution. Let S be the set of non-negative integers of the form A minus dq, where q is an integer. Here you can clearly observe that S hold the values of R, that is reminders. This set is non-empty because minus dq can be made as large as possible. So you can take proper values for q and that multiplied with d and subtracted from A will give us an element in S. Now by the well ordering property, S should have a least element R which is equal to A minus dq naught. The integer R is non-negative and we already know that its value lies between 0 to D minus 1. So that leads to a case that R is less than D. Suppose R is not less than D, then there would be a smaller non-negative element in S, namely A minus D into Q naught plus 1. Now when you solve this, it leads to A minus dq naught minus d. A minus dq naught, we can replace it the r, so r minus d will be greater than 0. Hence, there are integers q and r with r lying between 0 to d minus 1, so that we can represent a as dq plus r. Hence, it is proved